Hello, my name is Tomasz Kacprzak. I'm at the ETH Zurich. Welcome to my talk about cosmology from large-scale structure with artificial intelligence. Before we start, I would like to quickly introduce our interdisciplinary team of cosmologists and computer scientists, specifically our excellent PhD student Yanis Fleury, machine learning expert Aurelian Luki, and data scientist Nathaniel Perudin. We all work together on these projects I'm going to show today. So let's get right into the topic. Large-scale structure is a powerful cosmological dataset, a unique time window into the late time evolution of the universe. Recently, the cosmological parameter measurements started to reach the precision levels comparable to that of the CMB. And stage 4 experiments will provide a treasure trove of data, a great opportunity for discovery, as well as a great analysis challenge. On the other hand, in recent years, artificial intelligence methods have experienced a tremendous growth, providing us with available and ready tools. In this talk, I would like to show how we can harness the power of artificial intelligence to make more precise parameter measurements from LSS from the current data, as well as how we can aid and accelerate the analysis of future data sets. So increasing the precision of measurement is what it's all about, especially in the light of recently observed tensions between the late and early universe, for example, in the sigma-8 parameter between Planck and Kids. All right, so cosmological information from LSS comes from pattern and structures in the cosmic density field. In this image, you're probably very familiar with of the Millennium simulation. You can notice that these patterns are very complex. They create this cosmic web of halos, filaments, and voids. And also, other artificial intelligence methods draw their power from the ability to construct very complex models, train millions of parameters, and capture very complicated patterns in the data. That makes artificial intelligence methods such as convolutional neural nets or deep learning a perfectly suitable tool for modeling and analyzing LSS data. So this is where the advantage of AI for LSS comes from, its ability to create these complex nonlinear patterns. So how do we use these tools in practice? We discussed two applications today. First will be to make cosmological parameter measurements from LSS data with AI. And the second is to aid the generation of cosmological simulations using generative machine learning models. So if you would like to generally measure some parameter constraints from our large-scale structure data, for example, with gravitational mass maps, we have some theory that with parameters we would like to constrain. We use that theory to make some kind of prediction, and we compare it to the data, and from that we get our cosmology measurement. Traditionally, this is done using a chosen summary statistic. For example, most commonly the two-point functions, power spectrum, or correlation function. And the theory prediction is then tailored for this summary statistic. So this theory can be analytical or semi-analytical. And this one statistic is used for comparison in a Bayesian framework to put constraints on parameters. So the power spectra and other hand-chosen summary statistics will always only probe a specific part of information that's contained in the data. Power spectra will capture only the Gaussian information. And there is, as we saw in the previous Millennium simulation image, quite a lot of information that is highly non-Gaussian in the density field. So this is an example of a light cone shell that we use in our cosmological simulations, which on the left from the n-body simulation with PKD graph, and on the right, this Gaussian random field draw with the same power spectrum as the image on the left. So you can see that the complexity of patterns that the Gaussian random field can create is much smaller than the one in the dark matter density. And this is the part complexity we want to harness to make more informed parameter measurements. Now, in this new inference paradigm, we would like to use machine learning tools to automatically detect features that are present in the data that will be useful and informative for a cosmology measurement. Instead of choosing a fixed statistic, designing it ourselves from using our intuition, we let the machine find the most informative and relevant patterns. This comes, of course, as a cost. We need to feed the machine with stimulations directly. So we can only do it for a grid of simulations in a smaller parameter set given by our computational cost limitations. So just to note, there were other summary statistics that were designed to probe the non-Gaussian information. For example, 3-point functions, Minkowski functionals, and peak statistics. They're all very interesting, and there's also, I'm working on some of that kind of analysis too. What is fundamentally different about deep convolutional neural nets and AI tools in general is that it uses automatically designed features. So with that, potential for improvement coming from AI, we ask ourselves a question: how much exactly will we gain using deep learning analysis? So in this first feasibility study led by Yanis, we used a relatively simple neural net, and we performed an apples-to-apples comparison between a power spectrum analysis and a convolutional neural net analysis on a stage 3-like survey setup for weak lensing. And we noticed that for a kind of a reasonable assumption about smoothing scales, we gain around a 40% increase in the constraining power using convolutional neural net compared to the power spectra. And this is a very significant gain, given that we would need roughly twice the amount of data to reach the same advantage using power spectrum only. So this is very promising. We also explored different survey configurations and different quality of theory prediction that we will be able to use for deep learning measurement. So if our quality of our simulations will dictate our smoothing scale, so of course our ability to simulate small scales will have a huge impact on how much we can gain. And of course, the noise coming from the survey depth and survey size will also impact the quality of measurement on the observation side. What we found out is that, as we expected, if we include smaller scales in our measurements, so our smoothing scale is low, the deep learning gains more. It gives a bigger advantage over power spectrum. If we increase the smoothing scales, we lose the advantage. On the other hand, if we vary the noise level, the results are consistent. The advantage is maintained. So even for relatively noisy data sets, deep learning captures more information. This is the previous plot summarized in on a curve. So on the smoothing scale is on the x-axis, and the advantage of the deep learning analysis compared to power spectra on the y-axis. So higher is better. And if we go to small smoothing scales, of course, the CNN advantage gets really significant over power spectra that has access to the same scales. So equipped with this promising forecast, we proceeded to making the first measurement of cosmology parameters from KIDS 450 data with deep learning. And this was a tomographic setup this time, and we used a relatively deep residual neural net and predicted the parameters for omega m, sigma 8, and intrinsic alignment amplitude. There was a blinded analysis, so we did not look at the results until we were completely sure that our simulation and analysis methods are robust. We tested a number of scenarios where we varied simulation parameters just to check if networks are robust to that. And most of the, pretty much all the standard parameters in simulations don't play a role. So deep learning's robust learning features that are actually physical rather than specific to a given simulation setup. Of course, we found that baryon models have very significant impact on kind of one borderline for this measurement, but for the future will have definitely a significant impact. So this was a limitation in the given analysis. So with that, we unblinded the results, and we found that a new constraints on KIDS 450 data using deep learning. We also compared it to our own power spectrum analysis in a apples-to-apples way again. So as we expected, on the left side, we see that CNN-based measurement is smaller than the one we achieved with power spectrum by the amount we expected it to have, around 40%. Also shrunk the degeneracy direction a little bit in the S8 omega m banana shape. And we also found that we, compared to other measurements, we found slightly higher sigma 8 and slightly higher intrinsic alignment amplitude. So our measurement puts sigma 8 slightly higher than the main kids for 50 measurement. So that is a very promising result. And with that in mind, we proceeded to thinking about the future. And of course, we will need a much improved simulation grid. So building a fully numerical theory prediction for lambda CDM will be necessary for this deep learning methods to be applied. So I led the CSCS production project called Measuring Dark Energy with Deep Learning, which is a collaboration between ETH Zurich, University of Zurich, and the Swiss Supercomputing Center. So this data is currently being finalized, and we use it for putting deep learning-based constraints in future lensing data. Also, what we will need is to work on the sphere, given that survey area is becoming large. So we developed this convolutional neural network framework that is a public code that encodes hill peaks pixelization and allows to build deep learning models. In the second part of the talk, I would like to talk about using AI to generate simulations for cosmological applications. So even now, for measurements based on power spectra, we heavily rely on n-body simulations calibration, so for the nonlinear part. And this is typically done by creating emulators of the P of k. And examples are, for example, Euclid emulator, Cosmic Emu, or Baco. And they're very fast and very precise emulators built on n-body data. To reach the needed precision levels, we need to use simulations. Whatever we do, whether it's a power spectrum-based analysis or a deep learning analysis. And in the spirit of building emulators, we thought, why not try to build an emulator for the mass maps themselves for a given survey scenario? So we worked on this in a series of papers, but in the latest paper we published, we used conditional generative adversarial networks, which is a type of generative AI, which we trained on a grid of simulations shown here in this picture. And that was done in a conditional way, so that we can ask, once the generator is trained, we can ask it to give us an example mass map at any point inside the grid. So it can interpolate between the points in terms of inside the generative model. And more importantly, this emulator captures both the signal, so how the mass looks like, and its variability, so how the mass differs if we use different random seeds, but keep the cosmology fixed. So we tested both the aspect of how accurate we are modeling its signal and the variability using generative adversarial nets, and performed a very extensive series of tests. Of course, we started with a visual comparison. And for different cosmologies, GAN and n-body images of mass maps look practically indistinguishable. Note that these 4 cosmologies are chosen so to be at different parts of this parameter space. You can clearly see the difference by eye. And also performed quantitative analysis, which was done using standard summary statistics using cosmology, power spectra, bispectra, Minkowski functionals. And also importantly, we compared covariance matrices of power spectra that come from a sample of maps generated with n-body and with GANs. These points shown here are for cosmologies that were not included in the training set. So this is testing the ability of the network to interpolate in this data space. Finally, this is a comparison of how stable these results are across the entire cosmology grid, and we used all sorts of different metrics to compare. The metrics in the bottom row show the typical cosmological summary statistics, power spectra, correlation matrix, and bispectra. And the top show machine learning or computer vision quality metrics such as structural similarity index and Fresher inception distance and Wasserstein 1 distance that was on the pixel that is created on the pixel histogram. All these values are normalized such that a 1 sigma shift will have a value of 1 on this color bar if everything was a Gaussian distribution. So it gives a little bit of intuition about the scale of problem here. And we mostly match all of these quality metrics to a couple of % across the entire simulation grid, with the exception maybe of a bispectrum, which has some regions where it's matching a bit worse, and some extremes there in the structural similarity index as well. So generative adversarial nets we demonstrated as a tool for generating density fields or maps of density fields. And there was also quite a lot of work on simultaneously generating different types of observables in one go. For example, in this excellent work by the team in Portsmouth, GANS were demonstrated to be able to predict multiple observables at a time, such as dark matter over density field and gas field, internal energy field. And so this can be also potentially used to in-paint baryon feedback models onto dark matter simulations and basically test enable also small scale inference using simulations and deep learning methods. This is a growing field. So there have been a number of papers demonstrating how cosmological simulations can be helped with use of deep learning or AI. I think this is going to be playing a more important role in the future due to this fantastic ability of AI to generate nonlinear models. This is the end of my talk. Thank you very much for your attention. Just to point towards several ways to go forward with machine learning in cosmology, I think we are moving towards the computational cosmology, where more and more aspects of the analysis are done numerically. And with that, we can actually try to reach the information floor of cosmological datasets using AI. This is due to their feature of automated pattern extraction and using this AI tools for cosmological inference. We will use large-scale simulation grids. So the construction of these grids is computationally very expensive. So I think large collaborative efforts will be quite important here, especially publishing data to the community. And together with building the simulations, we can try to understand our astrophysical effects in simulations better. For example, baryonic feedback or other types of effects can be modeled using simulations and AI. Finally, one last thought is that the advances in AI will continue to accelerate, I think, due to powerful applications in industry. And a lot of these tools are being made public to the community, especially for scientists. So I think we can capitalize on this progress and reap this long-hanging fruit of using AI for increasing our precision of cosmological measurements. Thank you very much.